Good afternoon, everyone. My name is Naing Min Than. I am from Myanmar, and I am a second year master student. Today, my presentation title is Developments of Autonomic Position Detection System by Space-Spectrum Sound in Greenhouse. This is today my presentation outline, introduction, problem statements, and objectives, materials and methods, expected outcomes, and next plan. This is the introduction. Nowadays, greenhouses are one of the main productive sectors of many areas of the world. In recent years, large-scale greenhouse facilities has been popular in Japan. Automated agriculture is important to increase food production efficiency. Automated ground vehicle is a key component of automated agricultural machinery systems. Accurate position and controlling system can be classified. System is critical for the performance of autonomous ground vehicle. About position detection methods, this is firstly I would like to present the position and controlling system. That is, can be classified into two parts. Both of them are depending on the position measurement methodology. And then there are many control methods for the vehicles, and indoor and outdoor have land maps, map matching, satellite-based navigation signal, and etc. Typical position detection method is GPS, laser, and sound system. Laser is a very high accuracy, very high cost, and so commercially used for in agriculture field is not possible. Another one is a GPS system. GPS system is a very high accuracy and very high cost. GPS is popular in outdoor environments. Indoor environments have a GPS is a large area. So we selected a sound system. Sound system is a very high accuracy and low cost. And then the problems of the detection methods by the sound waves. There is a sound velocity can change by wind and temperature and off cycle. This is my objectives: to find out the accurate position by using the base stationary methods in greenhouse environments. Accuracy goals is 1, L is 50 meter, error is 10 centimeter less or in greenhouse environments. This is a theory of the positioning methods using SS sound system. This speaker works like the image, and then microphones work the decibels, and then the image sound frequency, and then we can get time of flight, and then by using this formula, and then we can get like this distance. And then delta T is inputs of time and then the output of time. This is a two-dimensional base stationary methods. This method is I will use for my research. This is a speaker, and like this, and we will sense, and the target is here, and then this is a base stationary, and then the speaker emits like this direction, and like this direction, and speaker 3 like this direction, and speaker 4 like this direction. This becomes we construct as omnidirectional, because here is a cone and here is a speaker, and then the sound wave emits like and strike the cone, and then the sound waves go to this direction. And then we can get like this, and then the differential values is like, and then we can calculate by using this equation, and then we can get the targets of the position. And then this time I have no data, so I cannot decide how many times we should to calculate. This is a compensation method using a base station. Firstly, we should to know this. Firstly, I would like to present the advantage and disadvantage. This system has no need to measure temperature and wind velocity. Disadvantage is we should to fix positions, base station and MS speaker like this, and then we can calculate by auto detection positioning methods, and then we can get fix of this base station and MS speaker. And then how to calculate is like this. Here is a compensation method use a base station. This formula is calculation formula is distant this, and then we have including winds. So we can use like if we can use this formula, and then no need to measure wind velocity and temperature, and then we can compensate like this. Actually, our when we do research like this setting, sound frequency will be called this like direction. This is an experiment device. This is like a speaker. It's here, and the microphone like works a wireless receiver, and then this is a comb. This is also an experiment device. I will use 5 speaker for MS and bass, and then I will use a 6 microphone. One mic is set target, and then a base station, and then we will calculate. And then this is a experiment method. Place is a greenhouse, and then experiment areas I decided 20 meter like this, and then the distance from speaker to base from like here is I calculated 14.14 meter, and then I will measure the distance like this 9 measurements. I expected outcomes is once L is 50 meter, error is 10 centimeter or less. This is my plans. Now I am studying making a system. Then maybe I think that this end of June I will test and improve the system in July also, and then I will take data from workshop and outside environments this next month of end of July and August first, and then I will go and take data from greenhouse environments mid or end of August, because at that time it's a very hot condition, so the greenhouse will be some controlling fan or something, so I will take the summertime, and then the September is I will data correction. If I have time, I will go and take winter time also. Thank you.
Suggestion? Question?
How do you determine that when error 10 centimeters and distance 50 meters, that is your expected?
Yes, sir. Because like this here, actually last year we went some of the greenhouse. At that time, that lane is maybe I think 90 centimeter. So our robots have at least 75 or 80 centimeter. So our clearance is error. We can take 10 centimeter.
But then your experiment is conducted in 20 by 20 meters.
Yes, because if actually, for example, we can get 20 by 20, okay, our error is less than 5 or something, and then maybe multiply by 2 or something, we can compare to 50 meters onwards.
I think you can say that error must be less than 0.2%, for example. So you don't have to stick with the 50 meters. This is quite hard. You mentioned about 50 meters, but your experiment is only 20 meters wide. Okay, that's, I think.
Will you have any problems with the sound bouncing off of the walls and coming back towards the speaker?
Yes, but this system, because we use this system, based systems, firstly, we will note here this position, all of the position and phase, and then anytime we get from this sound velocity, and then we will use this velocity also like our targets. So other, how to say, reflections or some errors, maybe I think we don't need to consider it, because every time we use like this V, and then we compare and not to compare, like the differential value, and then I calculate like this. I think we need to calculate so many times, and then we can get the position, at least position.
Okay. Anything else?
In your experiment in August and maybe in December, are you also planning to have real obstacles, plants growing there that can potentially interfere with the...
No,
No.
I don't know.
Any other comments? Would you show us again your system with the base station? Which one is the best? Center one is the best?
Yes.
Then height is?
Height is a little lower this.
Lower?
Yes, because according to the dilation of precision, that's a GPS system I'm using. Maybe I think
Why lower? Higher sail is not good?
not good.
Why?
According to the dilation of precision.
Direction?
Dilution. DOP. Like this.
Yeah, explain about that.
Yes, because actually I didn't prepare it. So, actually in GPS we need 3 or more satellites, and then the receiver is here. So they calculated the like this DOP, and then every time not so different ratio, this receiver and the emitters. They published maybe I think the best one is 1 and 1:2 ratio is excellent.
I can't follow your explanation.
Yes. Sorry, I will explain later. Because
Anyone, you may explain about that?
Geometry accuracy basic is the we follow the effect of geometry. Basically, the more distributed the satellite or maybe the transmitter will be better. For example, like
Yeah, repeat.
For example, if we have like this one, so for example only 3, maybe 3 is enough. So if we have the area like this, so if we have distance from 3 satellites, so the possible position is here. So if we have a more distributed area like this, maybe this one is much smaller, so we can make a more precise. So that's why if we make the satellite or transmitter more distributed, of course it will be very good. So it's some measure, so they will some formula to calculate the value. So basically the less or smaller value of DOB is better. So this is a basic about DOB.
Yeah, I understand. But why base station should be near here, around here?
no, because for example, here for example, sir, this is a 2 meter. For example, base station should do 1.5 meter.
Why you couldn't do the 2.5? I'm asking you. You can hang down from the same, no? But you told us should be lower than that. What's the reason? Maybe it's okay. Okay. Maybe you have to make some model. How many meter would be good? Because Peter Sensei told us we have plants. Plants usually around up to here. So obviously, 1.5 meter is much obstacles. So higher places. But we know some autonomous vehicles, microphone might be higher or better or lower is better or some, which height. Well, what kind of height would be the appropriate? We have to design first. Then we have to determine what kind of plans. Depends on that. Anything else? Okay, thank you very much.